Hello YouTube, today I'm going to talk about the concept of finiteness in set theory. So our introductory question is, what is a finite set? Of course, informally we know that certain sets, like the set 235 consisting of the first three primes, are finite, while other sets, like the set of all natural numbers or the set of all real numbers, are infinite. But the question is, how can we actually formalize the concept of finiteness precisely? In this talk, I'm going to present three definitions, one from Cantor, one from Dedekind, and one from Kuratowski. So the first definition from Cantor stems from the intuition that we should be able to count the elements of a finite set with a natural number. In other words, a number from the set consisting of 0, 1, 2, and so on. As an example, we can count the elements of the set 235 with the number 3, and it seems pretty clear that we can't count the elements of the set of all naturals or the set of reals with a natural number, because no matter how large of a natural number I choose, there's always going to be more elements from those sets than I can count with that number. Of course, in trying to formalize this intuition, we immediately run into another question, which is, what does it really mean to count? Cantor formalized the concept of counting mathematically in terms of one-to-one correspondence, or bijection, although he didn't use the latter term. That was later introduced by Bourbaki. I'm assuming in this talk that you know what a bijection is. If not, now's a good time to pause the video and Google that. So the idea is that counting the elements of a finite set just means establishing a bijection between that set and some initial segment of the natural numbers. By an initial segment, I mean the set of all natural numbers less than some fixed natural number. And in this example, I'm actually going to exclude 0 from the natural numbers for simplicity, but I'll come back to that in a minute. So here's an example of a bijection, or an illustration of a bijection, between the set 235 on the left and the set 123 on the right, which represents an initial segment of the naturals. This is a bijection because I'm not mapping any two numbers on the left to the same number on the right, and I am mapping to all of the numbers on the right. You can see intuitively that the bijection correctly captures the counting process. If you think about what you would do if you were asked to count the number of elements in the set 235, you would be establishing something like this bijection in your head, or maybe out loud. By contrast, here's two examples of things that are not bijections. So if you look on the left, I've mapped the set consisting of 2, 3, 5, and 7 to the set consisting of 1, 2, and 3. I've mapped both 5 and 7 to the same number 3, but intuitively, I haven't correctly counted the number of elements in the set on the left with the number 3 because 5 and 7 are both mapped to the same number. On the right, I've mapped the set consisting of 2, 3, and 5 into the set consisting of 1, 2, 3, and 4, but I haven't mapped anything onto 4. This reflects the fact that I haven't correctly counted the number of elements in the set using the number 4. If I tried to map the number 5 to both 3 and 4, then I wouldn't even have a function, let alone a bijection. In summary, bijection does seem to be a correct formalization of the intuitive notion of counting. So this leads us to the following definition. A set X is said to be Cantor finite if there is a natural number n and a bijection between X and the set n sub n consisting of all the natural numbers strictly less than n. The number n, which can be shown to be unique, is called the cardinality or the size of X. And a set is called Cantor infinite if it is not Cantor finite, so that's just a logical negation. I want to make two remarks here. One is that we are including 0 in the natural numbers, and the other is that while I've attributed this definition to Cantor, it is also heavily influenced by von Neumann, in particular von Neumann's construction of the ordinals, but I'm not going to go into those details in this talk. So let's look at some examples. The first is somewhat trivial. The empty set is considered finite under this definition with cardinality 0. This is actually the motivation for including 0 in the natural numbers. If you take, in that definition, little n to be 0, then the set of natural numbers strictly less than it is empty, and the only set that is in bijective correspondence with the empty set is the empty set itself under the empty bijection. The set consisting of 2, 3, and 5 is finite with cardinality 3 because we can construct a bijection between it and the set consisting of 0, 1, and 2. The set n of all natural numbers is infinite under this definition. I'm not going to go into a detailed proof, but you can see why by considering any function that you might construct between an initial segment of the natural numbers and the set of all natural numbers. That function is always going to attain some maximum value, and any naturals greater than that maximum are not going to be in the image, and hence the function's not going to be surjective. So you're never going to be able to construct a bijection from an initial segment onto that entire set. If you want to make that argument formal, you need to use induction on the natural numbers. And of course, since the set of real numbers contains the set of natural numbers, the set of real numbers is also infinite. Under this definition, we can establish all of the familiar properties of finite sets. For example, every subset of a finite set is finite and of lesser cardinality. A finite set has only finitely many subsets. And finite unions, intersections, and products of finite sets are also finite. In fact, you can compute the cardinalities of all of these sets, but I'm not going to do that here. We also have the following important theorem. A set is finite if and only if there is no bijection between the set and any of its proper subsets. Recall that a proper subset is a subset that's not equal to the whole set, so some elements are missing. The forward direction of this theorem is fairly intuitive and is usually called the pigeonhole principle. It says that if you have a finite set, you're not going to be able to construct a bijection between that set and a proper subset. The reverse direction is a little bit less intuitive, and it says that if you have an infinite set, you're always going to be able to construct a bijection between the set and some proper subset. I'm not going to present the proof of this theorem because it's somewhat technical, but as an example, you can see that there's clearly no bijection between the set 2, 3, 5 and the proper subset 2, 5. However, the mapping that sends the natural number n to the natural number 2n is a bijection between the set of all natural numbers and the proper subset consisting of all of the even natural numbers. The theorem guarantees that this phenomenon always occurs for infinite sets. I do want to remark for those viewers familiar with axiomatic set theory that this theorem is a theorem in ZFC, and the reverse direction does make use of the axiom of choice. It requires at least countable choice. Because this theorem characterizes the finite sets, Dedekind adopted the property within it as a definition for finiteness. We state that here. A set is Dedekind finite if there is no bijection between the set and any of its proper subsets, and a set is Dedekind infinite if it's not Dedekind finite. You might wonder, given that Dedekind's definition is equivalent to Cantor's, at least in ZFC, but possibly slightly less intuitive, why would we ever want to use it? Well, there's several reasons. One, it doesn't require the concept of natural number to state Dedekind's definition. So with Cantor's definition, you need to either have the set of natural numbers in the background, or you need to construct them, for example, using the von Neumann ordinal construction. Either way, you need natural numbers to define Cantor finiteness. With Dedekind's definition, all you need is the notion of a bijection, so depending upon what context you're in, it might be easier to use Dedekind's definition. Also, we saw that Dedekind's definition is equivalent to Cantor's in ZFC, but if you're working in a weaker set theory like ZF without the axiom of choice, it's actually a more general concept. That is, every Cantor finite set is Dedekind finite, but not every Dedekind finite set is Cantor finite. So depending upon your axioms for set theory, you may want to choose Dedekind's definition to get a broader class of finite sets. This comparison naturally leads us to another question, which is, can we define finiteness without even the concept of bijection? The answer is yes. We start with the intuition that we should be able to obtain any finite set by starting with the empty set and repeatedly adjoining single elements. For example, we can obtain the set 2, 3, 5 by first adjoining 2 to the empty set to obtain the singleton 2, then adjoining 3 to that set to obtain the pair set 2, 3, and finally adjoining 5 to that set. It seems clear that we can't obtain the natural numbers or the real numbers in this same way. For example, although I can start with the empty set and adjoin 0 and then 1 and then 2 and so on, I'm never going to obtain the entire set of natural numbers this way. At least that's the intuition. There's definitely some underlying philosophical assumptions here about what sorts of processes I can and can't complete. To formalize this intuition, we're going to have to get a little technical. So what we're first going to try to do is construct the collection of all of the finite subsets of a given set X. We do this as follows. For a set X, let Finx denote the smallest set of subsets of X, which contains the empty set as an element, and is closed under the operation of adjoining to its elements single elements of X. Now that's a lot to process. You probably want to pause the video and read that a few times. Formally, Finx is defined as follows. It's the intersection over all collections of subsets of X that contain the empty set and satisfy this closure condition. Given any subset in the collection and any arbitrary element of X, the set that you get from adjoining that single element of X to the subset is also a subset in the collection. To make sense of this definition, you really have to go back to the guiding intuition. Intuitively, a finite subset of X is one that you can obtain starting with the empty set by repeatedly adjoining single elements of X. So if I have a collection C of subsets of X that contains the empty set and is closed under the adjoining of single elements of X, it's going to contain all of the finite subsets of X. Therefore, every finite subset of X belongs to this intersection. Conversely, the collection of all finite subsets of X is intuitively just one of the collections over which we're taking this intersection, because the empty set is certainly a finite subset of X, and if I have a finite subset of X and I adjoin a single element of X, I still have a finite subset of X. Intuitively then, Finx is the set of all finite subsets of X, so X is finite if and only if it belongs to Finx. This finally leads us to the definition of Kuratowski finiteness. A set X is said to be Kuratowski finite if X is in Finx, and a set is Kuratowski infinite if it is not Kuratowski finite. It shouldn't come as a surprise that this definition is due to Kuratowski, seen here wearing a hat. Connecting this definition with the previous definitions, we have the following theorem. A set is Kuratowski finite if and only if it is Cantor finite. Note this is actually a theorem in ZF and does not require the axiom of choice in its proof. Looking at Kuratowski's definition, we see that, like Dedekind's definition, it doesn't require the concept of natural number for its statement. But unlike Dedekind's, it doesn't even require the concept of bijection. In fact, it just uses elementary operations of set theory like intersection, union, power set, and so on. Also, in ZF, without the axiom of choice, we've seen it's equivalent to Cantor finiteness and hence logically stronger than Dedekind finiteness. So based on your needs, Kuratowski's definition could be extremely useful. I'll end by remarking that there are many other possible definitions of finiteness available, of differing levels of logical strength, at least in axiom systems like ZF. I encourage you to Google it and take a look at these various different definitions. Here are the specific references I used when making this video. In particular, I'd recommend looking at my notes on Leo Harrington's set theory course from UC Berkeley, which covers Kuratowski finiteness in more detail. That's not something that is as easy to find in most undergraduate set theory books. Thanks for watching.